Hello everyone, welcome to the ROB530 project presentation of Group 9. The topic for our project is implementation and performance analysis between two state-of-art SLAM algorithms, ROB530 and LSD-SLAM.
For our project, we decided to evaluate monocular camera visual odometry algorithms on a custom platform, the MBot Mini. The MBot Mini is a small two-wheel mobile robot used in the Robotics 550 course at the University of Michigan for developing a simple indoor 2D SLAM and autonomous navigation system. The MBot fuses odometry, the IMU heading estimate, and the LiDAR scans to localize the bot against an occupancy grid map, which is also generated from the LiDAR scans. In this project, we'll be taking the 2D pose estimated by the SLAM stack implemented in Robotics 550 as the ground truth for evaluating visual SLAM methods. Datasets in the form of ROS bags containing the ground truth information and the image sequence are produced by manually driving the MBot around a domestic indoor environment. The images captured are 640 by 480 and captured at 60 FPS. Note that the map created from the LiDAR scans experiences some drift over the course of looping around the home, as the MBot SLAM stack was not designed to operate in an environment with such irregular surfaces, such as windows and mirrors and bumpy floors. However, this level of accuracy suffices for our purposes, which is to validate the visual odometry algorithms, whose noise and drift factors can be a lot more prominent than these.
Now let's look at the ROB-SLAM. The orb here means oriented fast and rotated brief. It's a local feature detector. ROB-SLAM 2 is an open-source platform that provides robust visual, simultaneous localization and mapping. The algorithm uses orb feature mapping and key points for tracking, mapping, and localization. There are three threads working in parallel: tracking, local mapping, and loop closing. Tracking also determines which keyframes will be used in bundle adjustment. Local mapping uses the keyframes and executes bundle adjustments. New correspondences are chosen for future loop closures. Loop closing searches every keyframe and uses similarity transform to calculate the drift.
Here are some of the results of ROB-SLAM. The purple is ground truth data, and the blue is estimated pose from keyframes. The left graph shows a portion of the trajectory tracking for comparison with LSD-SLAM. There are no loop closures in this short example. The points plotted are from keyframes chosen by ROB-SLAM's algorithm, which shows fairly good tracking even with just visual odometry. The right graph shows a 3D map of feature matches. There are two highlighted portions circled in blue. The top shows where the algorithm stops tracking trajectory, which occurs when the MBot passes a window. After passing the window, ROB-SLAM still plots keyframes, causing a large cluster. And the bottom is when ROB-SLAM regains trajectory and feature tracking.
Okay, this is our LSD-SLAM. LSD-SLAM is a large-scale direct monocular SLAM. We have three parts here: tracking, depth map estimation, map optimization. The main difference between LSD-SLAM and feature-based SLAM methods are shown in the picture. For the first part, tracking, we optimize the total error to get the transformation, and we update the pose from transformation. For the second part, depth map estimation, we have two main steps. The first step is depth map refinement, and the second part is depth map creation. You can see more details here in the pictures. Finally, we can see the map optimization. You can get pose graph optimization from this part.
Here is the result of LSD-SLAM running on our own dataset. The red line is ground truth and the blue one is estimate pose of keyframes optimizations. The first two graphs show a portion of the trajectory tracking. For comparison with ROB-SLAM, the right graph shows a 3D map of generated point clouds and the path of the MBot. Current camera frame and history camera frame are shown in green, red box, and blue boxes respectively. The dataset is the same as what ROB-SLAM 2 used in the previous slides. The upper right corner of the slide shows the real-time trajectory of the mapping with real-time point clouds on it. From the plot comparison, we can see that LSD-SLAM estimates the ground truth not so well as ROB-SLAM 2 did on our dataset, but the result is acceptable. LSD-SLAM requires relatively high on the initialization of the tracking and does not work so well in the environment which lacks textures like close to the ground.
In conclusion, we modified ROB530 2 and LSD-SLAM and compared their performance on a custom-built MBOT. Some results we found are ROB530 has better estimation result with smaller tracking error, and LSD-SLAM can get a more dense point cloud generation. Also, LSD-SLAM can get implemented in real time and get direct estimation without feature detection. In the future, we will include more detailed comparison, like the number of feature matches between frames, number of good matches, speed of computation, error of pose data, and how long the algorithm takes between frames and overall time. We are also going to compare the algorithms using more other datasets available online.